third lecture today by Daniel Hambleton will explore some of the other aspects of Xenakis' very, very broad artistic vision. Daniel has been a scientific researcher here at the Fields Institute during the last year. He's a mathematician working in architecture, engineering, and the construction industry, and is involved in the relationships between mathematics and design. He has a consulting company, Mesh, which specializes in the use of geometric theory and technique in design, in particular in architectural design. Daniel is going to discuss the simulation of scientific phenomena in visual and acoustic arts, and in particular as developed in Xenakis' ideas and work. The title of his talk is Simulation as Inspiration.
Thanks, Ed. So I've, in contrast to the previous two speakers, I've actually never spoken about Xenakis before. So this is going to be very interesting for me, hopefully for you. Today I'd like to talk about simulation and sort of the role that simulation plays in the design industry. And rather than sort of focus on the very sort of scientific applications of simulation, I'm going to look at viewing it as a kind of an aesthetic jumping off point. So I'd like today I'd like to start by sort of contextualizing Xenakis, both in terms of his compositional work, but also in terms of the surrounding kind of architectural movement that was going on, and then also contrast it with some of the main mathematical features of the time. And this is going to be very quick, partly because there's this wonderful exhibit in the foyer about Xenakis' sort of life and times, and also because of the wonderful talks we've had today. So I don't want to duplicate any of this stuff. Also, I would not want to come between you and cocktails in the next sort of half hour, 45 minutes, which I understand is happening. So. The second part then is going to be broken down into three segments. I'm gonna zoom out even more than what James did previously, and really talk about the very basic structure of how Xenakis viewed sounds and the sort of basic constituent elements of his compositional technique, and use that to springboard into generative design, basically, as a whole. And then get up to sort of some of the contemporary examples of design in terms of architecture and how it overlaps with engineering. And then the last part is kind of a bit of fun, and maybe I won't say anything more about that until we actually get there. So some of the surrounding sounds. Of course, Shostakovich in Russia, although this time I'm not sure how much contact Shostakovich might have had with the rest of Europe, but it's one of my favorite composers, so I put him in there. Olivier Messiaen. Pierre Schaeffer. John Cage. And of course, Stockhausen. architecture, around this time, we're sort of there was this growing tension between the modern and the postmodernist movements. Of course, Xenakis was employed by Le Corbusier, an absolutely staunch modernist. Some of the other big names, Mies van der Rohe here with his Barcelona house. Frank Lloyd Wright, America, with the Guggenheim. And of course, Le Corbusier with the Savoy Pavilion, I think, house, where you can see some of the defining features for Le Corbusier's office, at least. These, why put a wall in when you can make it a row of columns, and these sort of horizontal banded windows, sort of very defining features of his office. And of course, later in Xenakis's, some of Xenakis's contributions to Le Corbusier's office is making the rhythm of these elements more interesting, but maintaining a sort of standardized construction logic to it. In math, there was a lot of sort of foundational work going on. There's a lot of excitement around set theory. You have at the beginning of the century, you have, of course, the Hilbert list of unsolved problems, which sort of generated a lot of excitement for the rest of the century, really, for the 20th century. You have some sort of foundational work in fast Fourier transforms, these sort of creating algorithms to actually do some of the problems that came up in the time. But probably more specifically, there are sort of three events, or maybe two events here, that I'm sure had a very profound, impact on Xenakis. Von Neumann actually formulates the principles of game theory, which Xenakis has used in his later compositions. And Kolmogorov axiomatizes probability theory. So probability theory, and this is, of course, we've heard a lot about the stochastic processes in Xenakis' music, but this is a really key mathematical result. And probably not coincidentally, it happened in 1933. So not long after this, Xenakis started using probability theory in his music. So, I'm sure the two are related. Anyway, the point with the Kolmogorov axioms is that while probability theory had been around for many years, it was always sort of formulated in these questions about urns. How many things can you pick out of other things? And it was a very discrete world. But Kolmogorov actually creates a framework to make this world a continuous one. So he creates these axioms that now smooths out these probability functions. Well, it allows you to define something called a probability function, which of course Xenakis uses all over the place in his work. And of course a huge Kurt Gödel, little known fact that Gödel is actually spelled root delta, D-E-L. That's just a typo. It's not an inside math joke. And so in this mixture, you sort of squarely have Xenakis, 1922 to 2001, with some main features of his architectural life being the opening of the Unité d'Habitation, and of course the Philips Pavilion opening in Brussels in 1958. So I won't sort of talk about the man any more than that because of the fantastic previous lectures that we've had. So what is the basic structure of the stochastic music? So we've heard a bit about the application of it, and I'm not going to get too much into the mathematical detail here, but I do want to sort of very rigorously kind of define it as he defines it in formalized music. And let's skip that quote. So this is about as basic as it comes. This is the notation for a note. This is an interdisciplinary talk after all. I've got to start with the basics. Okay, so what's important to realize is that this is a notation. This is just a symbol for something. Underneath it, we can ascribe properties to this thing that we're notating. in music, when you see this note, a certain sound emanates depending on instrument and etc. And I feel that there are probably other ways you can measure a sound, but Xenakis settles on four. You have the timbre, or the musical family, that's producing this note, the pitch of the sound, basically just its frequency, the intensity with which it's played, and the duration with which it's sustained. So these are numbers. These are quantifiable numbers. I guess the musical family would be a bit tricky. You may have to take all the instruments and group them together and then number them, and then they have, that corresponds to a number. But these numbers are more or less continuous. You can have sort of infinite variations of any one of these numbers. And then there's a clear, if you define what you're hearing in this way, there's a sort of very clear relationship to coordinate systems. You can view these numbers as a vector, and so we throw away the problematic musical instrument coordinate and just view the three axes as consisting of the frequency, the intensity, and the duration with which this note is held. So this is the kind of the kernel of how Xenakis builds up the rest of his machinery. The fact that you can correlate this thing that you're hearing, even complex sounds can be broken down into these units. You can correlate what you're hearing with this coordinate system. And I think it's worth mentioning that actually correlates the wrong word. You can associate, or you can map these things from one to the other. But just because you can link two data sets doesn't mean there's any kind of causality here, right? And this has been mentioned all throughout today, that actually Xenakis would be the first one to say that you don't throw away intuition. You're not being forced into something. You're simply applying a new methodology to this, to musical composition. And I think of the kind of mathematical proverb that is that definitions are never wrong, only useless. And so here I think, due to the emanating bodies of work from this theory, that this definition was very fruitful. Okay, so Xenakis was quite unhappy with this determinacy in music, and there are more experts in musical history that can maybe tell you a bit more about that. But I take it to mean that it's this kind of deliberate placement of one note after the other, regardless of how you arrive there. So you sort of very much, this note is there because you've placed it there. And he was quite interested in saying, well, what if we don't really know where the notes are going to go? We just kind of know a region around in which these notes should appear. Well, this lends itself very well to being modeled with the newly formulated continuous theory of probability. And the way you can read this kind of archetypical bell curve graph is that on the x-axis you have the events that are going to take place. So any point here is related to an event. And these are the sonic events. These are going to be these points in musical space, which for Xenakis consist of those four coordinates that we talked about just a couple minutes ago. The frequency, the intensity, the duration, and I guess musical instrument. And you can then, of course, this is a simplification because the x-axis is a one-dimensional ordering, and so you'd have to find a way to map that more complex coordinate space onto this one-dimensional one. However, what you can read off from this is, given an event, you can read off the probability with which that event's going to occur. And from here, you can start to construct the grids of things and the organizational charts that we saw in the last talk that constitute the sort of macro structure of Xenakis' work. So another musical notation that comes up quite often and is a very excellent example And from this point on, we're going to try and build towards, we're trying to get into the sort of the architectural realm with these things. So the glissando lends itself very well to this. So this is the notation for a glissando, and it simply means that the instrumentalist will start at one note and sort of continuously vary up to another note. And of course, everywhere in his music, you can see this very heavily notated, the pivopracta in particular. And it may not look much on the musical score, but this kind of continuous line of sound, using his newfound notation for these sounds, is extremely graphic, and it lends itself very well to being sort of graphically plotted on coordinate systems. So I think at this point, anyone with like some spatial visualization can't help but look at this diagram and start to see structures and how would this fit in three dimensions, and I think really that's exactly what happened. Scott realized this sort of this aesthetic of the straight line being sort of continuously varied is then realized in the Phillips Pavilion. We're going to come back to the Phillips Pavilion in a minute. So, generative architecture is a pretty loose term, but it mainly pertains to designs that have grown out of principles or guiding rules. So you lay down a set of instructions for an algorithm or as a kind of layout for a procedure, and you iteratively apply these rules and instructions, and a form will start to emerge. To see why the structure that came out of the Phillips Pavilion is so particularly important, we have to take a brief detour into geometry and define what it means for something to be curved. So if you imagine yourself living on a surface, there's sort of two distinguished directions that you can think about, and those are the directions of maximum curvature and the directions of minimum curvature. Quite simply, you can start from where you're standing and test every direction a little bit, and you'll find that the direction where the surface bends most and the direction where the surface bends least are perpendicular to each other. So you have two directions, and more than the directions, you can also measure the degree with which this surface has been curved. And from here, you can start to investigate what sort of properties come out when you impose conditions on this measure. So there's sort of two very famous measures. There's the Gaussian and the mean curvature of surfaces. The Gaussian curvature simply takes so K1 and K2 are these directions of principal curvature that you're investigating on the surface. And these are actually the values with which the surface is curved. So you can, again, just define a measure of this curvature, this thing we're trying to study, and we take K1 times K2. And on an arbitrary surface, this is going to vary in any way, in any number of ways. It won't be constant unless you sort of very carefully controlled your surface. But you can ask, and this is a typical sort of mathematical approach, you can ask what happens when this measure is constant. What kind of family of surfaces coincide with Gaussian curvature being 0? And so that family of surfaces is called the ruled surface, and that's exactly the constituent surface with which the Phillips Pavilion is created. And a ruled surface is simply one that at every point on the surface there's a straight line that lies entirely on that surface. So that's an interesting geometrical property. But from an architectural point of view, and especially from a construction logic point of view, it's hugely important. You now have a very logical construction of the surface. And notice actually, especially in this diagram, there's no surface to be seen here. Right? It's just an arrangement of these straight lines, and it's And it's their particular relationship that kind of gives this illusion of curvature. We're going to come back to that as well. And of course, you can develop these surfaces even more, which is something that of course Gary Partners did to huge success, both architectural and financial. You have these large arrays of what are called developable surfaces, and developable surfaces are a type of ruled surface. So they still have this property. At every point, you can take a straight line. You can find a straight line that lies entirely on the surface. But they have an additional property, and that is that if you kind of imagine taking adjacent straight lines for sort of in a continuous surface, this doesn't make a whole lot of sense, but you take a point here and you find its straight line, its ruling line, and then you take a point sort of close to it, you find its ruling line. Those two lines will be planar in a discrete way. And what this means is that you can unroll these surfaces without deviation onto the plane. And these are, that's an especially important property for manufacturing, because typically manufacturers have large rolls of things like steel or titanium. And getting it onto curved surfaces is a well-known problem. So these developable surfaces solve this quite neatly. Another distinguished measure of that you can do with these K1 and K2 values, these values of maximum and minimum curvature, is the mean curvature, which is defined as K1 plus K2 over 2. Again, you can ask what happens when this is 0, and you get the whole family of minimal surfaces. So these are surfaces that, given a boundary, this surface is the one with least area that spans that boundary. And although I don't think there are so many sort of realizations of minimal surfaces in architecture, they certainly made a large impact because of sort of unique properties and sort of very striking topological features. So it's actually very rare in architecture that you ever build anything curved. And I would probably say that it's at an architectural scale, on the scale of a roof or an atrium or a facade system, you will probably never build anything curved, simply because the molds don't really exist and the financial structure doesn't really exist to fabricate these types of things. So in the modern application of freeform geometry to architecture, there's this layer that has to be dealt with called the discretization of these surfaces. And that kind of interaction is actually where I do most of my work. But it also ties the design of freeform surfaces to geometry in a very fundamental way. So the question is very simple. You have a sexy surface that an architect has designed, and you are a contractor with a bunch of flat glass panels and ways of cutting them, and your task is to create that surface. And essentially, what you're doing is you're just trying to kind of break down the design surface into smaller chunks, more manageable chunks. So you go ahead, and you may be successful, you may not be, depending on how difficult the surface is. But there's maybe if you're especially investigative, you might notice something very peculiar happening, and that is that if you take the vertices minus the edges plus the faces of the resulting discrete structure that you've created on your surface, you'll notice that for similar surfaces, this number is constant. You can see this very basic example if you take these 5 shapes, right? So these are So basically just the regular polyhedra. The point is that they're all kind of sphere-like. They can all kind of be inflated or sort of continuously deformed into a sphere. So there's this kind of maybe imprecise, as of yet, imprecise similarity between all these shapes. And yet, they are very different in terms of their discrete structure. Okay? But the point is that, again, you take this measure, this vertices minus the edges plus the faces, and you calculate that number, and you get 2's across the board. This number will be different for different surfaces, but it will be the same for those surfaces that kind of continuously deform into one another. And so this is called the Euler characteristic. So this, you can ask yourself then, well, what does this mean for construction? And this is a Massimiliano Fuchsas building in Frankfurt, and it's just like the perfect slide for this point. So you have this very interesting facade, which has been discretized and probably rationalized, and so many decisions have been made as to how you can do this. But remember that the Euler characteristic is at work here. So you can go in a triangular arrangement, you kind of want 6 panels coming from every vertex. This gives this sort of very regular checkerboard continuous line panel or pattern. But then you notice this guy, 1, 2, 3, 4, 5, 6, 7. And this, of course, aesthetically blends in quite nicely. But there's a fundamental point going on, and this is you can't get rid of this node condition. You can move it around, and you could maybe swap out some other edges and place it in a different spot if that's aesthetically not the best spot for it. But you can't get rid of it. Again, this is the architectural design being sort of subjected to the mathematical theory underneath. So, since Xenakis' time, there have been many curve structures that have been built, and all of them have their challenges. You can go from the purely triangulated approach to something that's maybe much trickier to do from an engineering and construction standpoint, but results in a much cleaner structure. This is the approximation of the surface with planar quads, to even funkier stuff, and so this slide is very interesting. This is from a group in Austria, a group of the Technical University in Vienna, who have made it their business to study the implications of curvature on surfaces. So, although architecturally this image, is a bit questionable, from a mathematical point of view, the incredible thing is, so remember in the Phillips Pavilion, okay, every smooth surface there was one of these ruled surfaces, and it's an amazing feat of draftsmanship and engineering that you can actually draw it at all by hand without computers. Here, each one of these strips, so you go around all of these things, is one of those surfaces. And it's not only a ruled surface, it's also a developable surface. So this can be sort of unrolled onto whatever material you like without distortion. And the importance of this image is just the sheer control and the sheer complexity of this arrangement. So this is something that really comes out of the modern usage of 3D modeling programs and custom simulations to get at these very complex arrangements. But how do designers kind of interact with these objects? And that's rhetorical question, but it's also a very difficult question. You know, these complex objects take a while to arrive at, given a certain design intent. But there's a lot of work going on now in the investigation of these so-called pseudo-physical forces that aim to encapsulate these geometrical properties in a simulation that wants to tend towards an equilibrium state. So this is the classic kind of physics simulation that I'm sure many of you have either seen in practice or just, you know, in video games, right, with all the particles going everywhere and the explosions. There they simulate things like you know, gravity and sort of explosive forces. The same logic and the same simulation can be used to simulate things like out of planeness or not equilateral enoughness. New word. So this is right, this won't come prepared though. This is some work done by a researcher in London called Daniel Piker, and his site is excellent. It's called Space Symmetry Structure. So this is, of course, a very well-known thing in math, the sort of circle packing. And all these things like, you know, equilateralization and planarity are encoded into a physics system, which you can then just use to push and pull points around. So the amazing thing is the amount of I guess, sort of construction awareness that's being embedded into this simulation. You know, you have a system that only responds to physical stimulus, but you've managed to encapsulate this kind of very geometrical quality inside of this simulation. Of course, once you get to the point where you can in architecture where you can encapsulate all these geometrical notions in a physical system, then you can also encapsulate any number of other notions. And this is a video that was just released a couple days ago from the Center for Information Technology and Architecture in Denmark, Copenhagen. So here's a kind of evolutionary structure that starts in a very settled condition and keeps trying to branch out. But in its branching out, it becomes unstable. And you can see it on the right there. It's reaching out for the ground or for the wall or for another sort of tendril in its system. And it seeks to move towards a stable system. So here, not only are you simulating this growth algorithm, but you're also, in real time, feeding it back into a structural analysis loop. And I think also simultaneously a construction diagram that lays out all the connectors and the individual pieces for this whole assembly. Being able to kind of quickly and easily and sort of continuously model all aspects of the design process, you know, design intent, this branching structure, how it performs under general loads and conditions, and then also how it's going to be built, how do you control the manufacturing aspects. Being able to do that seamlessly and in one environment is a very big problem in architecture today. And then I think just to show off, they scanned it in 3D. And so this is just the point cloud representation, which looks beautiful and, you know, could be used for verification of these processes. Okay, so some speculative development. So the first thing I'd like to do is just revisit so this is going to be a few sort of demos of things. First thing I'd like to do is revisit the Phillips Pavilion and kind of show in a little bit more detail how you can go about constructing these surfaces and really show that there's a strong generative logic underneath it. So this is my 3D modeling platform of choice. So we can start with a relatively simple construction. We can just draw sort of a line with a bunch of points, a bunch of control points, which we're going to use later. Okay, but we don't want to go ahead we don't want to model this whole structure by hand. We want to do something algorithmic. So this is a visual sort of code editor, essentially, which allows for sort of real-time geometrical operations to be done. First thing we're going to do is take those two curves and divide them into a certain number of points, which we want to control with a slider. What good is a visual design system if you can't have sliders? None at all. So you can look these things up, and of course, you have these nice little wires that tell you where everything's going, and all of a sudden we can control the division of these lines very easily. Okay, this looks nothing like the pavilion yet. However, if we do a relatively simple operation and just connect the corresponding points on line 1 to the corresponding point on line 2, we're going to up the density a little bit more. Turn off these things. So here we have a nice flat road. But because we've defined all the parameters in an algorithmic way, we can we have the very fun job of now pushing and pulling everything around until we get something sort of quite interesting. So we can start to push this up, and we get a nicely curved surface. And we can, actually I'm going to insert a control point here. Now if we move these up, and then this one down, you start to get a much more interesting shape. So this doesn't, I'm not trying to model this back into the exact form of the Phillips Pavilion, but it has all the same properties. You have guiding curves, and between each of these two curves, you have a nice set of ruling lines, which can be used to lay out structure or anything else. So I use Grasshopper all the time, and so this is a very fun exercise, but this is something that these types of programs and these types of tools kind of form the backbone of a lot of design technology today. So when I was reading through formalized music to think about Xenakis' formulation of notes in terms of spatial properties, I couldn't help but feel that most of the tools that exist to simulate these things now are very flat in many ways. Originally they were used to scan in pictures and drawings, but I think that's more just a result of the process of the day than any sort of particular rationale that that's the best way to do things. So the development that I thought I'd try and do is to take one of those simulations. Say a couple other things. That another theme that comes up in when Xenakis talks about his formulation and of these spatial points and how they can be related to other physical systems like the modeling of gas particles moving in a constrained area. He's also very critical of the state of the art of the time, which is fair. Computers hadn't really been around for too long. And they certainly couldn't do a lot of these very large-scale computations, and certainly not in real time. But that has changed quite dramatically. And this is one of my favorite recent simulations. So this is a fluid. It's an ocean, and it's composed of 5 million particles. And because it's a fluid, particles close to each other have an effect on each other, which means that in this system you have to have a concept of neighbors, which naively would mean that every particle has to check every other particle for some property and perform a computation based on that, which already right there increases the computational load to something extremely difficult. N squared is a very inefficient operation. There are ways to get around this, but the fact remains that this computation is an extremely heavy one. But we now have tools and techniques. We have very fast GPUs, graphics cards in our computers that can do this in real time. And I think Xenakis would probably be thrilled to see this kind of simulation. So that was a synthesized orchestra. That's a purely digital orchestra. And another one of Xenakis' beefs, as it were, was that existing sonic simulation technology just really wasn't very good. And probably that was true as well. And so much, I feel like a lot of the work with the distribution functions revolved around making the individual sounds that a synthesizer would play more realistic and more sort of in tune and more sort of human. And that maybe wasn't the case at the time, but I think now, although I don't think any synthesizer will be able to reproduce sort of the human element of performance, certainly there are some that are really quite good. And so the existing implementations of this space simulation stuff that I found, on the one hand, as I said, is kind of very flat. It sort of is very two-dimensional. And the other one is that they don't seek to make it sound, very, very nice. There's a lot of sort of experimental synthesized sounds at the microstructure, which is very interesting from a computational point of view. But from maybe a performance aspect, it would be nice to hook it up to a synth that sounded maybe very, very realistic. So, of course, these are some of the excellent current implementations of this spatial space-to-sound kind of translation. As was brought up earlier today, this field has taken off in a huge way, and so sort of live and mixed media installations are extremely common, and these are some of the major players providing functionality to perform that kind of installation. The other thing I thought about for the current simulation Xenakis' work is that it's not a lot of it is focused it's not a lot of it is geared towards architects or designers. Some maybe towards the kind of graphics design and media design, but for something that really grew out of this architectural experience, there's not a lot of translating architecture back into this stuff. And if so, it's definitely not in one of the most common platforms. It's for Rhino and Grasshopper. I think some of the current tools could be made more accessible by being implemented in environments that aren't so isolated. For instance, like Rhino, where most of the 3D modeling happens for most designers today. Anyway, all this to say, it's no good to kind of complain about this if you don't actually step up and try and do something. So last week I started coding this thing, and as a disclaimer, I'll say that I started with this kind of nice idea to make this sound simulator, and it was quite nice, and it had pretty pictures in mind. And then before I knew it, I was dealing with like bugs that I had no idea how to resolve, and writing sound buffers that just went astray and making some horrible noises. And arguably what I'm going to show today is maybe not too far from that. But at least it shows the connection from this very specific platform to somewhere that you can implement some more work on. So as just as an example, I'll just show that. So okay. Right. Okay. So let's just start here. To turn on my bounding box. I'm constrained by a 1024 screen here. I don't have the big array. Okay. So as a quick sanity check, we can just do the kind of hello world example, which draw a straight line. Here I've sort of stayed very close to the canonical implementation. So you have intensity on the y-axis, you have pitch on the z-axis, and well, there's actually currently there's no conception of time in the kind of coordinate system, but I'll get to that. So we can put it into we can model away happily, and with any luck, I should say that this thing has only been running stably for about, well, it doesn't run stably, but it's been running for about 3 hours, so. So there you go. There's a nice sort of visualization of these field lines. Those things come from something that actually was brought up in formalized music, and something that Xenakis got quite excited about in his book. That would be a way to simulate the charges, fields, and particles that have been charged with their gravitational or magnetic input. And so that's exactly what this thing simulates. And that can go back into the simulator. So again, it's very very rough, but as a proof of concept, you can get at the positional and MIDI information of any note that's flying around. You can change it to interpolate between the notes to create the glissando effect, and there's any number of other features you could implement. This is obviously nowhere near the existing implementations that are out there, but I think it's the only one that sits on top of a widely used modeling platform, which reconnect with architects might be interesting in and of itself. And it's all open source. I'd be happy to share it with you if anyone wanted to. C#. Yeah. So not Fortran. punch cards. So at this point, I'd like to just conclude. I think there was some question about sort of the relevancy of Xenakis' work and its influence on things today. And certainly one of the outstanding features of Xenakis' work for me is just the rigor with which he approaches his job, and the huge amount and deep respect for the fields that he comes across, and almost like paralyzingly so. And I think that's a huge point for all interdisciplinary work. There's a tendency to just kind of, on the surface understand something and say, oh, that's very nice. I'll just use that kind of pretty picture in something. And of course, as artists, you can do whatever you want, right? But I think the sheer rigor with which Xenakis approaches his mathematical formulation of sound is very inspiring for me, and goes to show what kind of great things can happen when you not just superficially but kind of fundamentally bring two fields together. So I'd like to say thank you and open up to any questions if anyone has any.
It's not really a question. I just wanted to specify one characteristic of the music which makes it unique even to this day. And we were extremely surprised to find out how unique it is to this day. With very, very recent research that was executed in the archives at the Iannis market. Two young scholars were husband and they went into the belly of the archives to realize that we were invited to participate in a special issue of Organized Sound that will be published in August of this year, so in a couple of months, to sort of put a finger to the pulse of where is you taken from the concept of everything else that's going on with all of the other dynamics and things like that you mentioned, I see. The specificity of UPIC is that it is the only one, even to this day, where through the machine you compose the sound as well as the score. And that is amazing because, as you said, with yours, which is great, and congratulations on your, it's great into this. You're using MIDI sound, you're using this and that. And I certainly agree with you that we can probably, with computational memory and everything else available today, we can improve the quality of the sound. But in workshops that we've done in places like FKM and in Karlsruhe, where there's very sophisticated machines, everybody loves the music for its vintage sound. So I just wanted to...
Yeah, that's great, yeah.
Where the composer designed the score. And that's pretty special.
Yeah.
We got other people in. In French, we have an expression, souvent imité, mais jamais égalé. Often imitated, but never surpassed. And we always thought that was true. But we thought somebody would try to imitate the fact that you can compose the sound also with the song. No.
Great. Yeah.
Sort of add to that and kind of go down the line of inquiry. With the software that you do have here, you could, instead of using like MIDI triggers, base the output on sine tones, right, and kind of use an approach to compose the sound using this software, right?
At the heart, there's actually, and this is what kept me up for 2 nights. There's one step where you actually write the raw buffer to the sound card. So this is the 4400 sampled values between -1 and 1. So you can do whatever you want with those. You could run that through any kind of DSP algorithm. I just use a MIDI trigger just because I didn't want to mess with that stuff. So yeah, and it's based on the sound font paradigm too. So there's a huge amount of open source material for that.
Maybe it raises the question of simulation, though I think we're using the term somewhat differently. And again, to return to Xenakis' composition, algebra, it was never about simulation. And to me, absolutely, I would argue, knowing your work in structural architecture, it's the most interesting stuff is where it's not about the simulation, the exploration of form, the exploration of the mathematics, or geometry is really the exploration of materiality, and in the same way that so we construct sound, or we build rather than simulate sound. Because failure, in a nutshell, of most of the digital universe is it tends to simulate rather than cut new tools we can operate in something quite unique. So, my reading of this is that MIDI sound without a convenience. And what's fundamental relationship you're able to establish using open.
Yeah, and specifically a reconnection with a tool that is very familiar to architects and designers. Most other, I think all other platforms really require the use of a little scripting thing, or they're very isolated packages, and so I think there's value to be gained in kind of building off of popular platforms and sort of and reconnecting. I mean, that's how you get energy behind a particular platform is building on an existing user base.
Just another quick one. Time is being treated parametric.
That's right. Yeah, I actually forgot to say that was another motivation too. Is I you can't get away that these things are sort of sound is passing through time, but I also wanted to get away from the scanning of things, so that you could just read shapes from the parametric level. Instead of a curve being sorted along whatever axis, and that's how you play it, you start at the start point of the curve, and it reads through that, which is a slightly more geometrical notion.
So if before the three-dimensional model was frequency, intensity, and time, if time is parametric, what is?
Nothing. Nothing yet. Yeah. There's any. You could have it drive something else. I just didn't implement it. So there's another coordinate free for stuff. Yeah. Yeah. Exactly. Yeah. Yeah. I had a heck of a time getting this thing running for today anyway, so. Cool.
Other questions? Well, I'd like to thank Daniel for a provocative view of Xenakis' work. And I would like to thank all of the speakers today who, in 3 or 4 very short talks, I think gave us a really marvelous view of Xenakis' ideas. And very, very pleased to be part of it. I'd like to thank the speakers and thank all of you for coming. As I said, you're welcome to join us for a little reception outside. We hope to see you at concert this evening at 8 o'clock. Thank you.